Physicists of the 21st century ask themselves, why did we have to invent a new physics, if classical laws already describe everything our eyes can see perfectly well? The answer is clear. Familiar models show no more than what appears on the surface. To glimpse what lies unseen, we must invent ideas that no one has ever envisioned before. Imagine one sensational hypothesis. Harvard professor Lisa Randall, whose books invite readers into the world of strings, writes about invisible dimensions that may explain the strange behavior of matter and antimatter. Here is a striking fact from her book Warped Passages. The extra dimensions in which strings and particles can move are not necessarily tiny and concealed. They may be vast, even infinite, yet still invisible. That becomes possible if space in those dimensions is curved in a very particular way. Such warping conceals them from our senses and our instruments, as though we inhabit a three-dimensional pocket of a higher universe. This approach offers explanations for puzzles surrounding matter and antimatter and even paves the way for experimental confirmation of extra dimensions. It is worth noting that Lisa Randall is a renowned American theoretical physicist, a professor at Harvard, and the first woman to hold a tenured position in this field at MIT, Princeton, and Harvard. Her scientific interests involve string theory, particle physics, and cosmology. In 2007, Time magazine included her on its list of the 100 most influential scientists and thinkers in the world. So, what is string theory? It is the attempt of physicists to explain how the universe is structured at the deepest foundation. The central idea is that all elementary particles, and even forces themselves, may be explained if we picture them not as points, but as tiny vibrating filaments, called strings. These strings are unimaginably small, about 1/1,000,000,000 of a centimeter in length. Depending on how each string vibrates, we perceive different particles: photon, electron, quark, and so on. The shape of vibration determines the properties of each particle. Mass and charge are not intrinsic points, but patterns of resonance in these hidden strings. So instead of familiar point-like objects such as electrons or quarks, the theory suggests everything consists of minute oscillating strands, invisible even to today's most advanced devices. Each distinct vibration of a string defines the type of particle and its traits, like its charge or mass. The idea of string theory began to grow during the mid-20th century. One of the most visible figures in this subject is Columbia professor Brian Greene, director of the Institute for Strings, Cosmology, and Astrophysics. Greene is also a major science communicator and author of The Elegant Universe. His 1999 book became a sensation, helping countless readers grasp the main ideas of string theory. In that work, Greene put forward the bold notion that our ordinary world of three space dimensions plus time is only a fragment of a far richer and more multidimensional reality. Those extra dimensions may be curled up so minutely that we never notice them directly, yet they play a key role in shaping the cosmos. Greene further explains that in string theory all particles are vibrating strings, and their properties are set entirely by how these strings resonate, much like notes on a musical instrument. Thus, fundamental particles, like electrons or quarks, are not points in space but tiny vibrational filaments, each producing a hidden melody. This changes everything. The material world is transformed into one vast fabric of vibration, resonance, an intricate cosmic symphony. Besides Greene, physicists worldwide study strings. Among them is Edward Witten, regarded as the leading theorist of our time, who earned the Fields Medal for mathematical advances tied to string theory. Both Greene and Witten see string theory as one of the foremost candidates for the elusive theory of everything. Naturally, scientists ask, why do we need such a complicated framework? The reason lies in the effort to reconcile quantum mechanics with gravity, an effort riddled with mathematical obstacles. String theory captured attention precisely because it offers a road toward unifying quantum mechanics with general relativity, two pillars of physics traditionally at odds. Greene details how string theory strives to merge the physics of the very small, captured in quantum mechanics, with the physics of the very large, Einstein's relativity and the structure of the universe. At present, no single experiment fully confirms string theory, but physicists are devising methods to test it in practice. The Large Hadron Collider, for instance, searches for predicted particles, including superpartners of known matter and force carriers, an area labeled supersymmetry. What is especially intriguing is that string theory demands the existence of extra dimensions. While classical physics contents itself with 3 dimensions of space and 1 of time, strings require 10 or even 11 dimensions to function consistently. Physicists believe that these added directions are folded into complex microscopic structures invisible to current equipment, like ultra-thin layers in a cosmic cake. In daily life, we think of the physical world as 3 axes: length, width, and height, plus time, ever flowing forward. String theory invites us to picture a far richer map. In this view, our reality includes 6 or 7 more dimensions beyond the usual 4, each so tiny that no eye or machine has yet perceived them. Physicists call these dimensions compactified. They are wound into invisible loops, like tiny labyrinths embedded in every point of space. A common analogy is a garden hose. From far away it looks like one-dimensional line. Only up close we notice its thickness, the hidden dimension rolled within. So the added directions of string theory are curled away like that, impossibly small to detect but crucial in shaping the universe. These compact structures may also have intricate geometry, influencing how strings vibrate. And their vibrations define the identities of the particles we observe. Thus, the possible forms of hidden dimensions generate different laws of physics in each possible universe. Modern theorists often use Calabi-Yau manifolds to describe such compact hidden directions, each space elegantly compressing 6 additional dimensions. These manifold surfaces are special mathematical objects, resembling convoluted, multi-layered labyrinths, too small to see directly, yet fundamental to the cosmos. They are named after Eugenio Calabi and Shing-Tung Yau. Calabi hypothesized their existence in the mid-20th century. Yau later proved the idea mathematically in the late 70s. First perceived as pure mathematics with no physical application, decades later they turned out to model perfectly the hidden dimensions required by string theory. Remarkably, these manifolds span thousands of possible forms. Each shape dictates its own set of particles and physical laws. Thus, hidden worlds may exist within every point of ordinary space. In addition to Calabi-Yau, scientists employ other structures, heterotic spaces, toroidal geometries, and more, each shaping how strings wind and vibrate. Among them are spaces folded like tubular or toroidal surfaces, where strings wrap in exotic patterns, producing unique properties. Taken together, the many possible constructions form the celebrated landscape of string theory, an immense catalog of mathematical universes. Each version represents a specific recipe for existence, with physics defined by its unique geometry. The vastness complicates the task of matching theory with observed reality. Developments gave rise to M-theory, an ambitious framework describing not just strings but multidimensional membranes called brins, floating within 11 dimensions. M-theory, introduced in the mid-1990s, unified 5 previously separate string theories into one grand 11-dimensional view of the cosmos. Here, fundamental entities are not only strings, one-dimensional filaments, but two-dimensional sheets, three-dimensional volumes, and higher brins, each shaping the fabric of the multiverse. Edward Witten revealed in 1995 that the older models were not rivals, but different limits of a greater whole. He also gave it the name M-theory, though the meaning of M is debated. Candidates include matrix, mother, mystery, and missing. M-theory now stands as a chief contender for the dream of a true theory of everything, promising to unify all forces and particles under one elegant framework. Yet a complete mathematical formulation is still absent. Large pieces remain unfinished, though progress continues. The theory's birth was a milestone, sparking the so-called second superstring revolution, driven by the discovery of dualities, mathematical transformations revealing unexpected links between distinct models. Dualities show us that what appears big may be viewed as small or strong as weak, relative facets of one ultimate reality. If you find M-theory fascinating, science communicators urge you to follow discussions, ask questions, and add comments, helping bring these difficult ideas into the public light. As a mental exercise, try to picture the world around not as solid objects, but as a hidden network of strings and membranes trembling in 11 dimensions. Supersymmetry, if confirmed, will reshape our worldview. It proposes that every known particle, electron, quark, photon, possesses an unseen twin. This principle links fermions, the matter-building particles, with bosons, the carriers of forces. They are two faces of one structure. So, the electron has a partner called the selectron. A photon has its opposite, the photino. Their difference is spin, an inner feature, half integer or integer. Spin is like an internal compass of the particle, influencing how it behaves in fields, not a literal spinning of matter but a quantum property. Fermions have half-unit spins, bosons have integer spins. Supersymmetry links the two, suggesting one may transform into the other under invisible rules. This doubling of the spectrum makes physics more consistent, solving puzzles of the Standard Model and explaining, for instance, the Higgs boson's mass. Imagine holding a simple brick, made of quarks and electrons. Supersymmetry proposes a heavy dark brick composed of their hidden partners. Such particles may in fact constitute the mysterious dark matter that fills the universe. Dark matter is unseen because it does not interact with light, but its mass exerts gravity strong enough to keep galaxies bound. Swiss astronomer Fritz Zwicky hypothesized it in the 1930s, when galaxy clusters moved as if far more mass were present than visible. Later, Vera Rubin in the 1970s confirmed that spiral galaxies spin at steady rates, impossible to explain without halos of invisible material. Today, cosmology estimates dark matter as 27% of the universe's mass energy. Ordinary matter is only 5%. The rest is dark energy. Physicists strive to detect possible dark matter particles, often assumed to be heavy, weakly interacting, and hiding in cosmic shadows. The challenge is their great mass. Supersymmetric partners may be too heavy to create in accelerators. If lighter, their influence would already be evident. That is why tests at the Large Hadron Collider examine collisions for missing energy or anomalous effects, clues to new particles. Other methods include monitoring gravitational waves with LIGO and space missions like LISA, or checking for deviations in gravity at submillimeter scales. Some speculative experiments even test whether microscopic black holes might form at particle accelerators, a dramatic proof of extra dimensions, were it to occur. Though no such signs have been found yet, scientists remain persistent and hopeful. Supersymmetry continues as one of the most promising theories beyond the Standard Model, waiting for experimental proof. If confirmed, it may open revolutionary technologies, controlling energy at quantum levels, creating exotic materials, or building more powerful computation. But such outcomes are still far off. For daily life, near-term effects will be subtle, knowledge, improved theories, and gradual application. Investigating string theory itself is far from simple. Its equations only work in multiple dimensions, 10 or 11, beyond anything we observe. The implication is that our familiar 4 dimensions are just the visible surface of a multi-layered structure hidden microscopically. Despite its purity and elegance, string theory has no direct experimental evidence. Still, some indirect predictions, such as patterns in gravitational waves, approach testability. The history of this search includes both failures and hopes, from Polyakov's 1980s models to modern simulations and global experiments. Leonard Susskind, one of the founders of the landscape idea in string theory, argues that the search itself addresses philosophy, why the universe is the way it is. Perhaps future advances, quantum simulators, sensitive detectors, will let us finally compare string theory with real data. For anyone eager to broaden horizons, engaging with such debates is valuable. Asking questions, following research, adding one's curiosity to the dialogue. In conclusion, string theory is a deeply complex but also profoundly inspiring vision. It unites mathematics, experimentation, and imagination. Even if its grand hypotheses one day prove false, the very attempt to explain the universe in terms of vibrating strings has already changed our picture of reality.